In 2015, a team of researchers from the Sun Yat-sen University, China, led by Huang Junjiu, revealed that they had engineered embryos, which are fertilized eggs between the 2nd and 4th week of development, to modify the gene causing the fatal blood disorder beta thalassemia. Beta thalassemia is a blood disorder that reduces the production of hemoglobin. This is an instance of germline genetic modification, where the modification can pass on to the developed adult. They utilized a genetic engineering technique known as the CRISPR-Cas9, which was previously discovered by scientists at MIT. CRISPR-Cas9 technology is used for gene editing, allowing researchers to easily alter DNA sequences and modify gene functions. CRISPRs are specific sections of DNA which has regularly repeated sequences of nucleotides. Cas9 is an enzyme which acts like a pair of molecular scissors capable of cutting strands of DNA and inserting a different DNA sequence or gene into a newly created binding site. This was the first time the technique has been used on a human embryo. The experiment was met with heavy international criticism. Prestigious journals including Science and Nature also refused to publish the team's scientific research paper on their experiments, largely because they believed the research to be unethical. An industry group in China called for a ban on such experiments, highlighting that genetic engineering to cure diseases may eventually become extended to scenarios such as designer babies and eugenics. Eugenics refers to selectively breeding humans to have more desirable heritable characteristics. The team claimed that they did not try to establish a pregnancy and that the embryos used, which were obtained from a fertility clinic, were non-viable, meaning that they were damaged and could not have further developed into a human. However, there is no concrete evidence to prove this. Furthermore, new research published in the scientific journal Molecular Genetics and Genomics in 2017 revealed that Huang's team is now experimenting with viable embryos, which raises even more ethical concerns as this concerns human lives. In lieu of these concerns, the ethical question being discussed in this video will be whether research on germline gene editing should be carried out on human embryos to prevent diseases.
There are many stakeholders in this case. The first stakeholder that we have identified are the researchers themselves carrying out the gene editing at the germline level to prevent diseases. In essence, the researchers want to see whether this technology can be utilized to prevent heritable diseases and to gauge its technology's potential for further applications that may result in beneficence for humanity. With rigorous research on germline genetic modification, although the technology may currently be very unpredictable, it is possible to improve the efficiency and methodology of the technology to make it viable for its application. In addition, it is likely that these researchers are sensitive to ethical concerns regarding the research they are doing, as it is their duty and responsibility as researchers to not merely look at the ethical implications of their research, but conduct research in a manner that reduces these concerns. In doing so, they need to ensure that through their research, no maleficence towards research subjects has occurred, or towards society in the long term. The second stakeholder are medical professionals looking to use this technology to benefit their patients to rid them of serious heritable medical conditions. Using germline manipulation of human embryos or somatic modification, however, it is a physician's duty to ensure that they do not harm their patient. Hence, they must wait for this technology to have little to no negative side effects on the patient's well-being after treatment. If this technology is complete, it is in the physician's interest to improve the quality of life of their patients. If this technology is able to be used in real life, the physician should have fairness towards his patients and make sure that technology is available to all socio-economic classes of society. The next stakeholder is those suffering from heritable diseases, who want to be cured, or those afraid that their children may suffer from heritable conditions and want them to be cured by germline modification. The main concern of these individuals is care for their young. These will entitle usage of germline modifications to cure their children of such diseases if and only if it has little to no other side effect on the child's physical or emotional well-being. This can be justified using the bioethical principle of beneficence towards loved ones, resulting in the need to rid them of potentially dangerous or life-threatening diseases. Finally, organizations, ethical boards, and governments around the world concerned about the ethical implications of this research are also a major stakeholder. One example of this is an industrial group in China which has called for a complete moratorium on gene editing experiments of this kind. These organizations want to make sure that the negative ethical implications of this research is reduced significantly. They want the harm caused by the research to be prevented and prevent the results from being misused, which can be attributed to the principle of non-maleficence. Scientific journals are also involved in a way that they have to prevent unethical research from being published in their journals. These ethical implications will be further discussed in our alternative options. With these stakeholders in mind, we will discuss possible solutions to the ethical question at hand. The first solution is to continue researching on germline modifications on embryos to remove gene codes for heritable diseases, so as to prevent the occurrence of such diseases. The second alternative is to allow somatic gene editing research on more developed embryos or other somatic cells to cure diseases instead of research involving germline genetic modification on very early embryos. And the third alternative is to not allow gene editing research altogether, whether germline or somatic.
The first alternative has benefits, seeing that germline modification of genes that cause heritable diseases may prevent these diseases from passing on in the individual and in further generations. This may allow for many people to be freed from the burden of such diseases and to have a better quality of life, and allows medical professionals and researchers to fulfill their needs. However, there are concerns on the ethicality and feasibility of the first alternative, regarding germline research being carried out on embryos and their infringement on several bioethical principles. Firstly, the research on embryos may infringe on the respect for human embryos. That is, solely creating embryos for research purposes is equivalent to treating them as a means to others' benefit. It is widely considered by ethicists, however, whether the same principles of autonomy and respect apply to human embryos, since they do not have interests or rights. Even so, these concerns are only valid provided that the embryos used for research are viable. A more important concern are the major risks associated with germline modification of the human genetic pool. This is due to the heritability of the genetic alterations induced, and as a result, all errors in modification may carry forward in generations to come. Especially since the researchers have found that there have been a number of off-target mutations in the experiments. This is clearly a worry in this context. Further, this kind of research shows how close we are to tinkering with the human gene pool. Ethicists are concerned that such research could spread quickly from non-viable embryos to viable embryos, at Huang, etc. did in 2017. The research could even be introduced in the market with risk of improper modifications, since it is difficult to assess the risk from mistargeted changes in the DNA sequence, which will affect both the treated embryo and any future generations. Now let us discuss the second alternative. In the past, much of gene editing research has been centered around somatic genetic modification, not germline. Regulatory bodies worldwide have also displayed a strong support and approved research for somatic cell genetic modification, since this type of modification and feasibility issues as discussed in the first alternative. This is because somatic gene therapy is done in the somatic cells of the patient, hence the new DNA does not enter the germ cells of the patient, causing the diseases not to be able to be treated within the patient and not pass on to future generations, hence reducing the negative implications in case there are undesirable errors after modification. This puts it at a lower risk level as compared to alternative 1, allowing medical professionals to fulfill their duty better. In addition, somatic gene editing research is already at various stages of clinical development and promises to be a powerful approach for many human diseases which do not have an effective treatment, while altering genes in human embryos can have unpredictable effects on future generations. Hence, this allows researchers to benefit humanity, and this alternative will concern ethical authorities less.
However, this may have its limitations. Should the modification be successful, the effects are still not heritable, and future generations will not be automatically ridden of this disease. Thus, further modification in future generations is needed to eliminate the disease for them. Ethicists worry that this extensive use of gene editing may create a two-tiered society of the genetically privileged and the genetically underprivileged, in which there is a divide between those who have the financial ability to pay for this use of this technology and those who are unable to do so, resulting in the violation of the bioethical principle of fairness. However, those affected by heritable diseases will still benefit from this treatment. In addition, should the research be carried out in late embryos, the autonomy of the embryo will be compromised, similar to disadvantage in the first alternative. Lastly, the third alternative considers not allowing research on germline or somatic gene editing. Such an alternative would prevent incidences of gene editing going wrong, and prevent the cause of dreadful side effects due to improper modification altogether. Additionally, due to the heritable gene alterations induced in germline modification, the worry that all errors will carry forward will be allayed by preventing such research as a whole. An obvious disadvantage to this alternative is that the promising development of gene editing technology to prevent heritable diseases from passing on to future generations will be halted. Thus, even though there is no risk in preventing such research, the prospect of beneficence to many people is reduced as well. Many ethical institutions worldwide do not support this approach, since the benefits do not outweigh the limitations. This is a big disadvantage to the researchers and medical professionals as well, as they will not be able to fulfill the duty and to the many heritably diseased people worldwide.
In conclusion, the second alternative is the most favorable since it maximizes the benefits of the therapy while minimizing its harms. This is as it has lesser risk as compared to the first alternative and is also able to rid patients of heritable disease, which the third alternative is unable to do. However, it may result in social inequality as discussed earlier, but this is not mutually exclusive to the first alternative. As such, research on somatic genetic modification on late embryos should be permitted to bring its benefits to the society. Any proposals to do germline genetic manipulation should be very carefully considered by the international regulatory bodies before it can be considered as a serious research prospect to reduce its risk if introduced to the